In Chapter 2.3, Functions with Domains, our objectives are to see an example of ordered pairs and the idea of function. 2 is an example of determining if an equation is a function using the vertical line test. We're going to see an example of determining a function from a graph, an example of evaluating a function, finding the x and y intercepts of an equation, and determining the domain of a function. Our first objective is to determine if a relation is a function. The definition is, given that x is related to y, a function of that relationship exists if, for each value of the independent variable x, has exactly one value of the dependent variable y. So in our first example, determine if the following set pairs are a function. So here we have it, a set of 2, 9, negative 1, 4, negative 2, 5, 3, negative 1. We will put that into a table to see if we have, for each value of x, there is just exactly one value of y. So for a 2, there is only one value, it's 9. For a negative 1, there's only one value, it turns out to be 4. For negative 2, there's one value, 5. And for 3, there's exactly one value, negative 1. So in this set of pairs, this is a function because there's exactly one value of y for each value in x. Now I want you to pause the video and see if you can determine whether the next set of pairs are in fact a function. So how would you do this? Well, I would put in a negative 1 here, negative 4. I'd put in 0, 0, a negative 1, 3, and 2, 5. Well, we see immediately that negative 1 for x shows up twice, and there are two different values for y. So this is not a function. Our second objective in this chapter is to use the vertical line test to determine a function. So we have an equation, x squared minus 4 is equal to f of x, right? And we want to determine if this equation is a function. So we will do the x-intercept and the y-intercept. For the x-intercept, we'll let f of x equal 0 and we'll solve. When we do that, we get x is equal to a plus or minus 2. So we plot those 2 points. We know for a quadratic equation, it's going to be a parabola, so there's going to be a vertex. And in this case, the vertex is going to be at the y-intercept. So when we put in for x equals 0, we get 0 squared minus 4 is equal to y. So y is equal to a minus 4. And we see where the vertex is. The vertex is right there. And so now we can use other points to find the rest of the graph, which we can do. And we see that we have a parabola. Now if we use the vertical line test, which is any straight line that we can pass through the function, and if this line only hits the graph at one point, at each point that I move the line through, we see that in fact we have a function. So this is is a function by the vertical line test. So now we're also going to determine if the following graphs are of a function. So we'll do number A first, and again we'll put a line through, and we see that no matter where we put the line through on this graph, we're going to get 2 points. So this is not a function. And the reason for that is because for each value of x, there can only be one value of y. And when the vertical line test gets more than 1 point, then it can't be a function for x. So let's look at B. We'll do the same thing. Well, there I get 1 point. There I get 1 point. There I get 1 point. And it looks like no matter how I draw my vertical line through any points along the function, it looks like, in fact, it is a function. So this is a function. Finally, we will do C. If we do a point here, we say, oh, well, that's a function. But now we do it along the y-axis, and we see that, in fact, we have 2 points that for when x is equal to 0, we get 2 different points. So this is not a function. So now we're going to evaluate a function. So our first function that we're going to evaluate is f of x is equal to x squared plus 3x. And we're going to evaluate it at -1, at 3, and -2. So when I put the value in -1 in for the function, I have -1 squared plus 3 times -1, which is 1 minus 3, which is -2. When I put 3 in, I get 3 squared plus 3 times 3, which is 9 plus 9, which is 18. And you can see I do the same thing for -2. I get -2 squared, which is 4, plus 3 times -2, which is a -6. 4 minus 6 is a -2. Now I would like you to pause the video and try the function kx is equal to the square root of x plus 1. 4 minus 1, 3, and 2. So you should have tried. So for our k of -1, we get the square root of -1 plus 1, which is equal to the square root of 0. So guess what? That's just 0. For k3, we get the square root of 3 plus 1, which is equal to the square root of 4, which is equal to 2. K at -2 is equal to the square root of -2 plus 1, which is equal to the square root of a -1, which is equal to I. Alrighty. So now our next objective is to determine the x and y intercepts. For the following function, determine the x and y intercepts. So we've done it for the first one. right? The x-intercept, I let g of x is equal to 0, and I solve for x. So 0 is equal to 3x minus 12. I add 12 to both sides. I get 12 is equal to 3x. Then I divide by 3, and I get x is equal to 4. So there is my x-intercept. And my y-intercept, we let x equal 0. So I have y is equal to 3 times 0 minus 12. So y is equal to minus 12. And here is our y-intercept. I would like you to pause for A and B and see if you can find these x and y intercepts for these two equations. So for our part B, for the x-intercept, we have 0 is equal to a negative x squared minus 9. We have 9 is equal to a minus x squared. And if we, oh, this is a plus, this is now a minus. Now we divide by a negative and we get 9 is equal to x squared. So this implies that x is equal to plus or minus 3. So in this case we have two x-intercepts. One's at 3, 0, and the other one's at minus 3, 0. Hopefully you got that. The x-intercept will just let y is equal to 0 squared plus 9. So y is equal to 9. So guess what? The y-intercept is at 0, 9. For the next problem, again, we let 0 is equal to the absolute value of x minus 2 minus 1. 1 is equal to the absolute value of x minus 2. So now we have two possibilities. 1 is equal to x minus 2, or minus 1 is equal to x minus 2. So in this case, we have x is equal to 3, or x is equal to 1. So we have two x-intercepts, 3, 0, and 1, 0. And then, of course, we have our x-intercept. So our y-intercept is going to be y is equal to the absolute value of 0 minus 2 minus 1. Y is equal to 2 minus 1. Y is equal to 1. So 0, 1 is our y-intercept. In objective number 5, we want to determine the domain and range from a graph. Here are some of the graphs that we have. We did the first one for you. So you can see that for this particular one, the domain for x is any value of x, which is in interval notation, is this symbol, parentheses, minus infinity, comma, infinity, parentheses closed. For the range, you can see that the value of the parabola, the vertex, is at 1, 2. So it starts at 2 and it continues in a positive direction. So we have a bracket 2 comma infinity. So I would like you to pause the video again, and I would like you to try B and C. Don't repause the video until you've got figured out what the domain and the range is. So let's look at B. Here we have kind of a parabola situation, but then we have a line going off in a different direction. It is a function because the vertical line test works in every single case. So in this case, the domain still seems to be all real numbers. Even with the discontinuity, you can see that there's still a point there, and that all the points are still there for all x's. For the range value, we see that the smallest possible value for y is a minus 10. So that should be a bracket, and we go in a positive direction from there. So there is our domain and range. C is a little on the tricky side in that there seems to be a closure point at 4 for x. So in this case, we have a negative infinity going to 4. Actually, there's a bracket at 4, isn't there? And then we can see that our range is very interesting. Our range looks like it's at 1. So it looks like it's at 1. And then actually it's 1 and then it's 2 to 4. So, or to 8, I'm sorry. It's actually to 8 in this particular case. So let me make sure I put this right. I believe that's correct. Yeah. Okay. So there it is. So here's our final objective, is to write the domain in interval notation. And here we're just looking at the domain. So we want to see whether or not x is restricted. So in rational functions, we will be looking at the denominators primarily. So you can see here that for a denominator, x minus 4 cannot equal 0, so x cannot equal 4. And so that means our domain is broken up into two pieces at negative infinity comma 4 and 4 comma infinity. For problem G, our problem here for the domain is there is a restriction in the numerator. We can't have an imaginary numbers in the real world. So we will have a restriction when, so this means that 3 minus x has got to be greater than 0. This means that 3 is greater than x, right? So x, or x is less than or equal to, actually, 3. So x is less than or equal to 3. So what that means for us is that we have a negative infinity up to 3, right? So there is our domain. In the last problem, again, we look at the denominator. Here we have 4 minus the absolute value of t, right, cannot equal 0. So essentially this is saying that 4 cannot equal the absolute value of t, so t cannot equal 4 or negative 4, right? So here we have the domain negative infinity up to negative 4. We have negative 4, comma 4. Then we have 4, comma infinity. So we've broken up the domain into 3 different places because we have t cannot equal 4 or t cannot equal minus 4 in this particular case. So that concludes our chapter 2.3 on functions and domains. And we'll probably begin on some linear functions next.